Chapter 19, Heat and the First Law of Thermodynamics. We will cover these topics in this chapter: heat as energy transfer, internal energy, specific heat, calorimetry, solving problems, latent heat, the first law of thermodynamics, the first law of thermodynamics applied, calculating the work, molar specific heat for gases and the equipartition of energy, adiabatic expansion of a gas, heat transfer, conduction, convection, and radiation. Section 1. Heat as energy transfer. Heat is not a material which is flowing from one object to another. Rather, heat is a form of energy, and the unit of it can be calorie, or CAL, calorie. 1 calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Don't be fooled. The calories on your food labels are really kilocalories. kcal, or calories, with the capital C. The heat necessary to raise 1 kilogram of water by 1 degree Celsius. If heat is a form of energy, it ought to be possible to equate it to other forms. The experiment demonstrated down here is a mechanical equivalent of heat by using the following way to heat the water. So, by definition, heat is energy transferred from one object to another because of a difference in temperature. Remember that the temperature of a gas is a measure of the kinetic energy of its molecules. Alright, now let's take a look at problem number 4 from this chapter as an example. A British thermal unit, BTU, is a unit of heat in the British system of units. 1 BTU is defined as the heat needed to raise 1 pound of water by 1 degree Fahrenheit. Show that 1 BTU is equal to 0.252 kilocal, which is equal to 1056 joules. To solve this problem, we have to assume that we are on the surface of Earth, so 1 pound is equal to 0.454 kilogram. So, based on the definition given in the problem, 1 BTU is equal to 1 pound at 1 degree Fahrenheit. And let's convert degree Fahrenheit and the pound into kilogram to the SI units. So we say 1 pound is equal to 0.454 kilogram. And 1 Fahrenheit is equal to 5/9 degrees Celsius. And 1 calorie, and that definition converts it into kilocalorie. So 1 kilocalorie divided by 1 kilogram, 1 degree C. And if we simplify it, so 1 BTU equals 0.2522 kilogram, which is almost 0.252 kilocal, as asked in the problem. And if you want to convert it into joule, 0.252 to kilocal, let's convert kilocal to 1 kilocalorie from the lookup table, 4186 joules. Do the calculations. We have 1056 joules. Section 2. Internal energy. The sum total of all the energy of all molecules in a substance is its internal or thermal energy. Temperature is a measure of a molecule's average kinetic energy, And internal energy is the total energy of all molecules. And as we defined, heat is a transfer of energy due to difference in the temperature. So now that we define the internal energy as a total energy of all molecules, so the internal energy of an ideal atomic gas is the number of atoms or molecules multiplied by the individual average of the kinetic energy of every single atom or molecules in our system. So the internal energy is N times 1/2 mv squared mean. But since we know the average kinetic energy in terms of the temperature, we can write the internal energy in terms of the temperature as 3/2 N, number of atoms, times K times temperature. K is the constant, Boltzmann constant. However, if the gas is a molecular rather than atomic state, we have to consider rotational and vibrational kinetic energy, and we should take them into consideration when we are calculating the internal energy. Section 3. Specific heat. The amount of heat required to change the temperature of the material is proportional to the mass and to the temperature change. So here, Q is the amount of heat required to change the temperature of delta T is equal to the mass of the material, M, times C, times delta T, change in the temperature. C here is the specific heat, which is a characteristic of the material. And here in table 19.1 on the left, for some material we have the specific heat listed here. The unit of C, the specific heat, is kilocalorie per kilogram per degree Celsius, or joule per kilogram per degree Celsius. For example, for water, we will see when the water is in solid state for ice at the temperature of -5 degrees Celsius, the specific heat is 2100 joule per kilogram degree Celsius. And when it's liquid at 15 degrees Celsius, it needs more heat to change the temperature. So we have more specific heat. It's almost double. And when the water is in the gas state or steam state at 110 degrees Celsius, it gets back to 2010 joule per kilogram degree C. Section 4. Calorimetry. Solving problems. For a closed system, no mass enters or leaves, but energy may be exchanged. For open systems, on the other hand, mass may be transferring as well. For isolated systems, closed system in which no energy in any form is transferred. For an isolated system, energy out of one part is equal to energy into another part, or heat lost is equal to heat gained. So here, the instrument on the left is a calorimeter, which makes quantitative measurements of heat exchange. Here we can see a sample is heated to a well-measured high temperature and plunged into the water, and the equilibrium temperature is measured. This gives the specific heat of the sample. Okay, as an example, let's take a look at problem number 8 from this chapter. An automobile cooling system holds 18 liters of water. How much heat does the water absorb if its temperature rises from 15 degrees C to 95 degrees C? To solve this problem, we should use the equation 19-2, which is the heat absorbed by the system can be calculated from that equation. So we say Q is equal to mc delta T. And we should note that for water, 1 liter is equivalent to 1 kilogram. Okay, have this one as a note. So Q is mc delta T. This is equation 19.2. Let's plug in the numbers. So we have 18 liter And let's convert liter into SI units. So 1 liter is equal to 1 times 10 to the minus 3 meter cube. Okay. And let's convert the liter into kilogram. So 1 meter cube is equal to 10 times 10 to the power 3 kilogram. Okay. Now let's multiply this by the specific heat of water, which is 4186 joule per kilogram degree C, and this is in the liquid phase, and multiply it by delta T, which is T2 minus T1. So T2 is the final temperature, it's going to be 95 degrees C, and T1 is the initial temperature, which is 15 degrees C. Okay, so if we do the calculations, we will have 6.0 times 10 to the power 6 joules. So this is the amount of heat that the cooling system is going to absorb from the system. All right, another example. Let's look at problem number 16 from the chapter. The heat capacity, capital C, of an object is defined as the amount of heat needed to rise its temperature by 1 degree C. Thus, to rise the temperature by delta T requires heat Q given by Q equals capital C times delta T. A. Write the heat capacity C in terms of the specific heat, little c, of the material. And B. What is the heat capacity of 1.0 kilogram of water? And C. Of 38 kilogram of water. All right, to solve this problem for part A, let's write down the two equations that we have. So Q is equal to mc delta T, and the equation in this problem is defined as capital C times delta T. Since the heat is the same from these two equations, let's put them equal. So on the left we will have m little c delta T. On the right we will have capital C delta T. And that delta T cancels out, and the capital C is equal to m times little c. Okay, so that's the solution to part A, which is the relation between capital C and little c, specific heat. For part B, it says what's the heat capacity of 1 kilogram of water. So we say capital C is equal to little m times little c, and that is 1.0 kilogram multiplied by 4186 joule per kilogram degree C, and that gives us 4200 joule per degree C. Okay. Part C, it asks for 38 kilogram of water. So we say capital C, m little c. Now we should multiply by what we got in the previous section by 38. So we will have 38 kilogram of water, and the specific heat is going to be the same, joule per kilogram degree C, and that's going to be equal to 1.591 times 10 to the power 5 joule per degree C. It's almost equal to 1.6 times 10 to the power 5 joule per degree C. Okay, so that concludes this problem. Section 5. Latent heat. Energy is required for a material to change phase, even though its temperature is not changing. For example, for the case of water changing phase from ice to water, this stage here, let's write it down, so draw a circle around it. From this stage, the temperature is increasing, as we can see, from minus 40 degrees to 0 degree. Temperature is increasing, the heat is increasing, added to the system from 0 kilocalorie to 20 kilocalorie, and we can see the temperature is increasing, but the phase does not change. From 20 calorie to 100 calorie at this stage, we are increasing the heat added to the system, but the temperature is not changing. And this is the latent heat, where the temperature is not changing. This is the heat needed to change the phase from ice to water. And then after the water has been formed and the ice has been converted into water, all liquid phase, at this stage we need more energy, or more heat should be added to the system, to the water we are considering here, to increase the temperature from 0 degree to 100 degree. And again, at 100 degree, we have a combination of water and steam, and if we increase the heat added to the system, the temperature does not change from 100 degree. So if you heat up a water which is already boiling, the temperature stays 100 degree, but water keeps evaporating until you reach the 740 kilocalorie. At this point, the water vapor is forming completely, and then we have the steam. So now that's the time we can increase the temperature from 100 degree to higher temperatures. So the heat of fusion, or LF, is the heat required to change 1 kilogram of material from solid to liquid. Okay? And the heat of vaporization, LV, is the heat required to change 1 kilogram of material from liquid to vapor. So the total heat required for a phase change depends on the total mass and the latent heat. So Q here is the total heat required, is equal to M, the mass, times L, latent heat. And in this table 19.2, we have the latent heats at different materials, different substances, and spend some time taking a look at this table here. To outline some problem-solving strategies for calorimetry, first we have to consider the question of whether the system is isolated or not. We should ask the question, are all significant sources of energy transfer known or calculable or not? Second, we should apply conservation of energy. So energy given is equal to energy converted or lost in the system. Third, if no phase change occurs, the heat transferred will depend on the mass, specific heat, and temperature change. And if there are, or maybe, phase changes, terms that depend on the mass and the latent heat may also be present. Determine or estimate what phase the final system will be in. 5. Make sure that each term is in the right place and that all temperature changes are positive. 6. There is only one final temperature when the system reaches equilibrium. And finally, considering all these 6 notes, solve the problem. So the latent heat of vaporization is relevant for evaporation as well as boiling. The heat of vaporization of water raises slightly as the temperature decreases. On a molecular level, the heat added during a change of state does not go to increasing the kinetic energy of individual molecules, but rather to breaking the close bonds between them so the next phase can occur. Okay, here I have problem number 24 from chapter 19 as an example. It says a 28-gram ice cube at its melting point is dropped into an isolated container of liquid nitrogen. How much nitrogen evaporates if it is at its boiling point of 77 Kelvin and has a latent heat of vaporization of 200 kilojoule per kilogram? We assume for simplicity that the specific heat of ice is a constant and is equal to its value near its melting point. So considering the strategy for solving problem here, and this is an insulated container of liquid nitrogen, the amount of heat lost by the piece of ice is used of the liquid nitrogen, and it's used to boil the nitrogen. Okay, so we say the heat lost by the ice cube is actually used to increase the temperature of liquid nitrogen and boil liquid nitrogen. Okay. We should add also the note that the boiling point of the nitrogen is boiling point of nitrogen is 77 Kelvin, which is equal to 196 degrees Celsius. Okay, now let's solve the problem. From the equation of heat transfer, so we call Q is equal to M for ice, C for ice, times delta T for ice, okay, is equal to M for nitrogen times L fusion heat of vaporization for nitrogen. Okay. For delta T for ice, we have temperature of ice initial minus temperature of ice final. Okay, so let's solve this because it's asking for the amount of nitrogen. So let's solve it for the mass of nitrogen. So mass of nitrogen is equal to the mass of ice multiplied by the specific heat of ice multiplied by delta T, which is T ice I minus T ice F, divided by capital L vaporization for nitrogen. Okay, let's plug in the numbers, what we have. So we have 28 times 10 to the minus 3 kilogram of ice. C for the solid state of water is 2100 joule per kilogram degree C. And for delta T, we have 0 degrees Celsius, and the final temperature of the ice is the melting point of nitrogen, which is 196 degrees Celsius. Okay. And actually, this is, there's something wrong here. Okay, my bad here, I'm sorry. So 77 degree Kelvin is equal to minus 196 degrees. So here, let's erase this part here. So we have 0 degrees Celsius minus the final temperature, which is minus 196 degrees Celsius. Okay, so this is the numerator. In the denominator, we have for L sub V vaporization of nitrogen, so we have 200 times 10 to the power 3 joule per kilogram. So if we do the math here, so we will get M for nitrogen equals to 5.8 times 10 to the minus 2 kilogram. This is the mass of nitrogen which is evaporating to reach the boiling point of nitrogen. Okay. Section 6, the first law of thermodynamics. the change in internal energy of a closed system will be equal to the energy added to the system minus the work done by the system on its surroundings. Delta E internal, which is a change in the internal energy of a closed system, is equal to Q, which is the heat added to the system, minus W, which represents the work done by the system on its surroundings. It is the law of conservation of energy, written in a form useful to systems involving heat transfers. The first law can be extended to include changes in mechanical energy or kinetic energy and potential energy. So on the left-hand side, we can say delta K, changes in kinetic energy, plus delta U, changes in potential energy, plus delta E, changes in the internal energy, is equal to the right-hand side of the first law of thermodynamics, which is Q minus W. Heat added minus work done. Section 7. The first law of thermodynamics applied. Calculating the work. Here, first we considered an isothermal process. Here, PV is demonstrated here. The temperature is not changing in each curves, the red curves A to B. As we can see, the temperature is constant, the higher T. And if the temperature is changing to a lower T, we will see we have another curve. But everywhere along this PV curve, the red line, temperatures staying constant. So for an isothermal process to take place, we assume the system is in contact with a heat reservoir. In general, we assume that the system remains in equilibrium throughout all processes. On the other hand, for an adiabatic process, there is no heat flow in or out of the system, into or out of the system. Here is a PV plot or the graph of an isothermal versus adiabatic process. We will see the slope for an adiabatic process is larger as compared to an isothermal process. But for the adiabatic process, there is no heat flow into or out of the system. Moreover, we have an isobaric process where we have pressure constant during that process. On the left-hand side, we have an isobaric process from A to B. We see that the pressure remains constant while the volume is changing and the temperature should be changing. On the other hand, on the right-hand side here, we have a graph of isovolumetric one, where the pressure is changing but the volume stays constant, moving from A to B. The work done in moving a piston by an infinitesimal displacement is given as dW equals to F dot dl. Force is a vector and dl is a change in or displacement is a vector, and they are multiplied together. And we know force is given as pressure times the area, P times A, and A times dl is actually changes in volume. So we can write dW as pressure times changes in the volume. For an isothermal process, P is equal to nRT divided by V. This is the ideal gas law. And if you plug in this equation into the equation for work from the previous slide, and we can do the integration to find the work done in taking the gas from point A to point B, as shown in this PV plot down here. So if we take the integral, we say work is equal to the integral of P times dV from volume VA to volume VB, from VA to VB. And nRT are constants coming out of the integral. We have the integral from VA to VB of dV over V, and this is the natural log of V from the initial point to the final volume of VB, and we will have nRT multiplied by the natural log of VB over VA, and this is the work done in taking the gas from point A to point B in an isothermal process for an ideal gas, by the way. You might consider a different path to take the gas from state A to the final state B by going through an isovolumetric process from A to D, and then through an isobaric process from D to B. Through the first stage of A to D in isovolumetric, there is no change in volume. Therefore, there's no work done by the system. Then the gas goes from D to B at constant pressure, where the pressure is constant. If you take the integral will be W is equal to the integral of P dV. P is a constant, so we have P, the integral of dV, from VD to VB, and this gives us P times delta V, changes from B to D, and change from V to D is equal to VB minus VA. Okay. So here we are listing a summary of various thermodynamic processes in table 19.3, considering the first law. For example, for the isothermal process, the first one, the temperature is constant and there's no change in the temperature because the temperature is constant, and it becomes no changes in the internal energy. Therefore, from the first law of thermodynamics, the heat added to the system is equal to the work done by the system. On the other hand, we have isobaric process where the pressure is constant, and that leads to the amount of heat is equal to internal energy plus the work done. Or instead of the W, we can put P delta V. Isovolumetric process, there is no change in volume, and therefore there is no work done, so the heat is equal to changes in internal energy. Adiabatic process, finally, where the case of no change in the heat, therefore the internal energy is equal to minus W. Alright, at this point, let's take a look at problem number 32 from the book as an example. An ideal gas expands isothermally, performing 4.30 times 10 to the power 3 joule of work in the process. Calculate A, the change in internal energy of the gas, and B, the heat absorbed during this expansion. So for part A, changes in internal energy of the system, this is an isothermal expansion, okay? Delta T is equal to 0. There's no change in temperature. Therefore, delta E internal is equal to 0. This answers part A. For part B, the heat absorbed during this expansion. Write down the equation for first law. Delta E internal is equal to the Q given minus work done. And note that the work is done by the system, or by the gas here as a system, so W is positive, okay? So let's solve this equation, the first law of thermodynamics, for Q, because it's asking for the heat absorbed. Q is equal to changes in internal energy plus W. As from part A, delta E internal is 0. Therefore, Q is equal to plus 4.30 times 10 to the power 3 joule. Another example, let's take a look at problem 44 from the book. How much work is done by a pump to slowly compress isothermally 3.2 liter of nitrogen at 0 degrees and 1 atm to 1.8 liter at 0 degrees Celsius. Alright, this is an isothermal process, and it's asking for the work done. So let's use the equation 19.9 for the work done by ideal gas during an isothermal process. So W is equal to nRT, natural log of final volume divided by initial volume. And from the ideal gas law equation, we know PV is equal to nRT. So we can plug in the PV value into this equation. So let's plug in the values. The initial pressure is 1 atm, which is corresponding to 1.013 times 10 to the power 5 Pascal, multiplied by the initial volume is 3.2 liter, which is 10 to the minus 3 meter cube, multiplied by natural log of the final volume 1.8 liter divided by the initial volume 3.2 liter. If we do the calculations, we will get minus 186 joules. This is the work done. So the work done by an external agent is the opposite of the work done by the gas. So this W is the work done by the gas, and if you want to see how much work is done by the pump, W, work done by pump, which is an external agent, is the opposite, which is plus 186 joules. And that solves the problem. Section 8. Molar specific heats for gases and the equipartition of energy. For gases, the specific heat depends on the process. We can simplify our discussion if we use molar specific heats CV or CP, defined as the heat required to raise 1 mole of gas by 1 degree Celsius at constant volume or at constant pressure. So we call it C sub V or C sub P. And therefore, the heat Q needed to raise the temperature of N moles of gas is written as N times CV delta T or N times CP delta T. So it is clear from the definition of molar specific heat that CV is equal to M times CV, where capital M is the molecular mass of the gas, and CP and CV are specific heat for constant volume and constant pressure. So here we have listed all the specific heats of gases at 15 degrees Celsius, and we see that the specific heats for gases with the same number of molecules are almost the same. And also we see that the difference between CP minus CV here is almost exactly equal to 2 in all cases. These numbers. For a gas in a constant volume process, no work is done. So Q sub V for isovolumetric process is equal to delta E internal. For a gas at constant pressure, QV is equal to delta E internal plus the work done, which is P times delta V. Comparing these two processes for a monoatomic gas, when the temperature change is the same, gives Cp minus Cv equals R, which is consistent with the measured values. In addition, since delta E internal is equal to 3/2 N times R times delta T, and we can write it down as N times capital C sub V times delta T, we can write C sub V as 3/2 R. This is also in agreement with the measurements. However, for a gas consisting of more complex molecules, diatomic or more, the molar specific heat increase. This is due to extra forms of internal energy that are possible, for example, rotational or vibrational degrees of freedom. As I said, each mode of vibration or rotation is called a degree of freedom. The equipartition theorem states that the total internal energy is shared equally among the active degrees of freedom, each accounting for 1/2 kT. The actual measurements show a more complicated situation. For solids at high temperatures, C sub V is approximately 3R, corresponding to 6 degrees of freedom, 3 kinetic energy and 3 vibrational potential energy for each atom. Here you have molar specific heat at constant volume for different structures or different atoms. For example, for diamond or beryllium, copper or lead at different temperatures, we see a more complex behavior because we have more degrees of freedom involved. Okay, at this point, I'll look at problem number 52 from the book as an example. A certain monoatomic gas has specific heat C sub V equals to 0.0356 kilocalorie per kilogram degree C, which changes little over a wide temperature range. What is the atomic mass of this gas, and what gas is it? So since the gas is monoatomic, the molar specific heat is given by C sub V is equal to 3/2 times R. And the molar specific heat is also given by capital M, the molar mass, the molecular mass times Cv, which is the specific heat. Let's write it down here. This is the molecular mass, and this is the specific heat. Okay? So let's plug in the numbers and solve this one for the molecular mass. Capital M is equal to 3R divided by 2 CV. 3 times R, which is 8.314 joule per mole Kelvin, divided by 2 times the specific heat given by the problem, which is 0.0356 kilocalorie per kilogram times degree C. Now let's convert kilocalorie into joule. So we say 1 kilocalorie is equal to 4186 joules. And now let's convert kilogram into grams. Of 1 kilogram is equal to 1000 gram. And that gives us, for capital M, that gives us 83.7 gram per mole. And if you look up a periodic table for an element with this molecular mass, we will note that this corresponds to krypton. Krypton has a molecular mass of 83.8 gram per mole, and that answers the question of what gas it is. Section 9. Adiabatic expansion of a gas. For an adiabatic expansion, the changes in internal energy is equal to minus P delta V, the work done. There is no heat transfer. From the relationship between the change in an internal energy and the molar heat capacity, we can write delta E internal is equal to N CV delta T. And from the ideal gas law, or we can differentiate the ideal gas law as P times delta V plus V times delta P equals N and R are constants, and we have NR delta T. Combining and rearranging these equations here, we can have Cp divided by Cv multiplied by P times dV plus V times dP is equal 0. All right, I'm just going to write down the equation from previous slide here. So we had Cp over Cv times P dV plus V dP equals 0. Now if we define Cp over Cv as gamma constant, we will have, let's write it down here, gamma P dV plus V dP equals 0. Let's do some rearrangement by taking a dividing everything on P times V. We will have gamma dV over V plus dP over P equals 0. And now if we take the integral from both sides, we will have gamma natural log of V plus natural log of P. And if we take 0, the integral of 0, we will have a constant. Okay? We know from the law of natural log, gamma times ln of V is equal to ln of V to the power gamma. And if we have the addition of two natural logs, it means that we have the natural log of the multiplication. So we will have, so instead of the first part, we say natural log of V to the power gamma. And we have addition of two natural logs, we say this is equal to the natural log of P times V power gamma. And this is equal to a constant. If we take exponential from both sides, P times V to the power gamma is equal to exponential to the constant, which is another constant. Okay, that's what we have here. The multiplication of P times V to the power gamma, which is the ratio of Cp over Cv, is equal to a constant. Section 10. Heat transfer, conduction, convection, and radiation. Heat conduction can be visualized as occurring through molecular collisions. The heat flow per unit time is given by delta Q divided by delta T equals K times A times delta T divided by L. As we can see here in the cartoon down here, We have the hotter side with a temperature T1, and we have a cooler side with a temperature T2. The distance between these two temperature points is equal to L, and the cross section of the heat flow is capital A. And we can see the heat is flowing from the hotter part, from the hotter side to the colder side. The constant K in the previous equation for the heat flow is called the thermal conductivity. And we have listed here in table 19.5 the thermal conductivity for some substances. Materials with large K are called conductors. Those with small k are called insulators. Most metals are good conductors. For example, silver, copper, aluminum, steel, they have larger conductivity, thermal conductivity. On the other hand, we have air, wood, brick, and these have very low thermal conductivities. And they are used, or they are considered as insulators or thermal insulators. For building materials, we define R values rather than thermal conductivity, and that is defined as L divided by K, and K is the thermal conductivity and L is the thickness of the material. Here in this table down, we have R values for some materials like glass, brick, plywood, fiberglasses, and other insulators. For different thicknesses, we'll have different R values, which is related to the thickness and the thermal conductivity. It's more relevant parameter. Convection, on the other hand, occurs when heat flows by the mass movement of molecules from one place to another. It may be natural or forced. Both these examples are natural convection down here. So here in the left we have a heat source, fire, which is heating up the container, and the water down here is getting hotter, and the molecules of water are moving inside a container, and they move upward, and the colder water molecules move downward. Or on the right, we have a furnace which is heating up the water inside the tubes in a radiator, and the hot water is circulating the water inside the building, in all the rooms and all the floors, and that radiator radiates and emits the heat to the building, which cause the hot air molecules to circulate inside the house and make it warmer. Now, the radiation is the form of energy transfer we receive from the sun, or if you stand close to a fire, most of the heat you feel is radiated as well. The energy radiated has been found to be proportional to the fourth power of the temperature. Delta Q over delta T is equal to epsilon times sigma times A, which is the area, times temperature to the power fourth. The constant sigma is called the Stefan-Boltzmann constant and is given as 5.67 times 10 to the power minus 8 watt per meter squared times Kelvin to the power fourth. Epsilon, the other constant in that equation, is called emissivity. And this is a number between 0 and 1 characterizing the surface where black objects have an emissivity of 1 or near 1, while shiny ones or surfaces have an emissivity near 0. This is the same for absorption. A good emitter is also a good absorber. If you are in the sunlight, The sun's radiation will warm you. In general, you will not be perfectly perpendicular to the sun's ray, and you will absorb energy at the rate of, for example, 1000 watt per meter squared epsilon A times cosine theta. And the cosine theta is the angle we're forming with the rays from the sun. And the area that the sun is being shined on is A, the area of our body. The cos theta effect is also responsible for the seasons. As we know, the axis of rotation for the Earth is tilted toward the sun. The sun rays are not normal to the ground. So we have some axis, and this axis is 23 degrees, for example, in June. And we have, for example, in this scenario here, we have the summer solstice in June, or we have in December, we have winter solstice. Okay, and that is the responsible for the seasons in the north hemisphere of the Earth, or we have the 6 months difference between the north and the south hemisphere. That is because of the cos theta effect, the angle which the rotation axis of the Earth is making with the direction of the sun's rays. So thermography is the detailed measurement of radiation from the body and can be used in medical imaging. Warmer areas may be the sign of a tumors or infection. Cooler areas on the skin may be a sign of poor circulation of the blood. Summary of Chapter 19. Internal energy refers to the total energy of all molecules in an object. For an ideal monoatomic gas, the internal energy is equal to 3/2 N times K times T temperature, or equals to 3/2 nRT. Heat is the transfer of energy from one object to another due to a temperature difference. Since heat can be measured in joules or calories, specific heat of a substance is the energy required to change the temperature of a fixed amount of matter by 1 degree Celsius. In an isolated system, heat gained by one part of the system must be lost by another. Calorimetry measures heat exchange quantitatively. Phase changes require energy even though the temperature does not change. Heat of fusion is the amount of energy required to melt 1 kilogram of material. Heat of vaporization is the amount of energy required to change 1 kilogram of material from liquid to vapor. The first law of thermodynamics states that the internal energy changes is equal to the heat given to the system minus the work done by the system. Thermodynamic process. Adiabatic, no heat transfer. Isothermal, constant temperature. Isobaric, constant pressure. Or isovolumetric is constant volume. Work done is equal to dW equals P pressure times dV, the derivative of volume. Molar specific heats Cp minus Cv equals R. Heat transfer takes place by conduction, convection, and radiation. In conduction, energy is transferred through the collisions of molecules in the substance. In convection, bulk quantities of substance flow to areas of different temperature. Radiation is a transfer of energy by electromagnetic waves.